Welcome to the Explainer. Today, we're jumping right into the core ideas of practical statistics. We're going to follow the journey data takes from just a pile of raw numbers all the way to some really powerful insights. So let's get started. Before we even talk about big data or AI, it all comes back to this one simple, powerful idea from a guy named John Tukey, a real pioneer in statistics. The idea? Just look at the data. That's it. It's not about fancy algorithms right off the bat. It's about getting your hands dirty, about exploring. Honestly, you could say the entire field of data science is built on this one thought.
So, where do we start this journey? Well, it starts in the chaos. Think about it. Most data out there is just a mess. It's unstructured, a jumble of images, random text, website clicks. The first job, and it's a big one, is to wrangle all that chaos into something neat and tidy, a structured table. You've got rows, which are like individual people or records, and columns, which are the features about them, like age or what they bought. You have to do this first. Nothing else can happen until the data is organized.
Okay, so our data is all neat and organized. Now, the fun really begins. We move into what's called exploratory data analysis, or EDA for short. This is exactly what it sounds like. We're exploring. We're getting a feel for the data, trying to see what kind of story it's starting to tell us. And the very first thing you'll probably want to know is, what's a typical value here, right? We're looking for the data's center of gravity, a single number that can kind of represent the whole group. Statisticians have a name for this, of course. They call it an estimate of location. It's basically our anchor point. But which average do you use? This is a really important choice. We've all heard of the mean. That's the classic average you learned in school. The problem is it's super sensitive to extreme values, what we call outliers. Imagine you're calculating the average income in a neighborhood, and then a billionaire moves in. Suddenly, that average income is ridiculously high and doesn't represent anyone. That's where the median comes in. It just finds the dead center value in the list. The billionaire doesn't skew it. That's why we call the median more robust. It's tougher. It's not so easily pushed around. Okay, so knowing the center is great, but it's only half the picture. You also need to know how spread out everything is. Are all the data points packed tightly together around that center, or are they scattered all over the place? This idea is what we call variability. It's the difference between a dense, packed city and a wide, sprawling suburb. Both might have a center, but they feel totally different, right? And this quote just nails it. This is why variability is everything in statistics. It's not just about finding the average, it's about understanding the spread around that average. When we see a difference between two things, is it a real difference or is it just random noise? Figuring that out, that's the whole game. It's how you make smart decisions. All right, so we've got a feel for our data's center and its spread. What now? Well, this foundation lets us move from just looking around to actually testing things. We can take our hunches and turn them into real hypotheses and see if the data backs them up. And the classic way to do this? The A/B test. It's such a simple, elegant, and powerful method. You just come up with a hypothesis, something like, I bet this new headline will get more clicks than the old one. Then, here's the key part. You randomly show one version to half your users and the other version to the other half. You measure what happens, and you compare. That randomness is the secret sauce. It makes sure that if you see a difference, it's actually because of the headline and not because one group just happened to be more click-happy. So let's make this real. Imagine a website is testing two different prices. Okay, at first glance, price A looks like the winner, right? 200 sales versus 182. But hang on. Look at how many people didn't buy. We're talking about tens of thousands of people. The actual difference in sales is just 18. So here's the million-dollar question. Is that tiny difference a real thing that will happen again and again, or did price A just get lucky that day? And there it is. That's the core question of all statistical testing. How do you tell the difference between a real effect and just random chance? How sure can we be that price A is actually, for real, better? To answer that question, data scientists have a special tool called the p-value. Now, this can sound a little complicated, but the basic idea is pretty straightforward. You start by pretending there's no real difference at all between the two prices. You assume it's a tie. That's the null hypothesis. Then the p-value answers this question. If it really was a tie, what are the odds we'd see a result this lopsided just by random luck? If that probability, the p-value, is super, super low, then you can say, yeah, probably not just luck. There's something real going on here. Okay, now we get to the part that feels like magic. We've explored our data, we've tested our ideas. Now we can use everything we've learned to actually predict the future. This is where data science starts to feel like having a superpower, for sure. So, in what we call supervised learning, that just means we're training a model on data where we already know the answers. Predictions usually come in two main flavors. First, you've got regression. That's when you're trying to predict a specific number. Think, what will the price of this house be? The other flavor is classification. Here, you're predicting a category. Is this email spam or not spam? Will this customer leave or will they stay? So for those classification models, how do we know if they're any good? We use something called a confusion matrix, and the name is perfect because it shows you exactly where your model is getting confused. It's just a simple chart that shows you what the model predicted versus what actually happened. It counts up all the times it was right, but also, and this is key, it shows you the types of mistakes it's making. And looking at that matrix often highlights a huge common problem. Think about something like credit card fraud. It's super rare, right? Maybe only 0.5% of all transactions are fraudulent. Now, you could build a model that just says not fraud for every single transaction. Guess what? That model would be 99.5% accurate. Sounds amazing, but it's completely useless because it would miss every single case of actual fraud. That's the rare class problem. And it's a perfect example of why just looking at accuracy can be totally misleading. So everything we've talked about so far, we had a target. We were trying to predict something specific. But what if you don't? What if you just have a mountain of data and you're wondering, are there any natural groups in here? Any hidden patterns? This is where we step into a different world. Unsupervised learning. And one of the most popular tools for this is an algorithm called k-means clustering. It's pretty cool how it works. You basically just tell it, hey, I think there are about, say, 5 groups in this data. You pick the number k. Then the algorithm just goes to work. It shuffles all the data points around over and over until it finds the best possible groups, where everything inside a group is super similar and the groups themselves are as different from each other as possible. It really is like an automatic sorting hat for your data. But okay, so you have these clusters, so what? They're just collections of data points. The magic happens when you investigate them. You look at what makes each cluster unique and you give it a personality. For instance, if you clustered stock market data, you might find one cluster is energy stocks are up, but tech is down. Another might be everything is up. All of a sudden, these abstract groups become meaningful insights about different types of days in the market. You've turned data into stories. And that brings our entire journey full circle, right back to where we started. It doesn't matter if you're building some super complex predictive model or just looking for hidden patterns. It always comes back to that first, most important step, just looking at the data. It's about building your own intuition, your own feel for the project by exploring first. So when you boil it all down, from exploring to predicting, all of these powerful techniques, they're really just tools to help us be more curious in a structured way. They're built on that one single foundation. So the real question isn't about the algorithms. It's this: what hidden story is waiting to be discovered in your data?